Good morning. My name is Ryan Berke. I am an assistant professor at Utah State University, and I'm here to talk about non-contact deformation measurements at extreme temperatures using ultraviolet digital image correlation. Now, extreme temperatures play a role in a growing number of engineering applications. In the energy field, for example, solid oxide fuel cells used to operate at temperatures on the order of about 800 degrees C, although I know there's been a lot of effort to bring those temperatures down. In the nuclear field, one of the Gen 4 reactor designs was the very high temperature reactor, VHTR, which had outlet temperatures on the order of 950 C. And then in the aerospace field, during either sustained hypersonic flight or spacecraft reentry, the leading edges of the vehicles are expected to reach temperatures on the order of 15 or 1600 degrees C. Extreme temperatures also play a role in a number of disasters in recent memory. So in civil engineering, the World Trade Center collapse happened when the steel beams were heated on the order of about 800 degrees C. Fukushima meltdown was when there was a loss of coolant, the fuel rods, the cladding was exposed to temperatures on the order of 1100 C. And then the Space Shuttle Columbia accident was during reentry, so that again was on the order of about 600 degrees C. So in order to design against any of these applications, we need materials that can survive those sorts of challenging environments. And in order to have confidence that the materials work, we need to characterize them using strain measurement techniques. So now in principle, measuring strain seems pretty straightforward. So what you see here is a pretty standard load frame, not a Gleeble, unfortunately. But you've got some sort of a specimen between two grips. One end is fixed, the other end moves. And then you've got a load cell there that monitors as you try to move one end of the specimen. And so in principle, the crosshead, it applies some sort of vertical motion and it reports what it is. The load cell measures and reports what kind of force it measures. And then if you just divide the crosshead displacement by the specimen length, you get a measurement of strain. But the problem with this sort of approach is that the force you apply is not isolated in the specimen. So if you think of this system like a series of springs, yes, you're stretching out a specimen, but you're also putting a little bit of stretch into everything else. And so if you divide that total change in length by the length of the specimen, the material is going to appear softer than it actually is. So there's a few different methods to more directly measure strain. Number one is you can use an extensometer, which is a gauge that just clips onto the side of your specimen. As the specimen deforms, then this gauge detects a change in length, and you can divide that length by the initial length to get strain. And this is a more direct measurement. Our Gleeble uses an LVDT. It's a pretty similar sort of measurement. It's a grip-to-grip measurement. Method two is you can glue on a strain gauge. So this is a device that you just kind of bond onto a surface. It's relatively small, so it's approximately at a point. And then as the gauge deforms, the resistance changes as a function of strain. So you can monitor the gauge with a Wheatstone bridge to monitor changes in resistance. And then finally, the third technique, the one I'm here to talk about, is digital image correlation. The basic premise is you've got an object you know you're going to deform. You apply a high contrast surface pattern, and then you record images before and after you deform it. And then an algorithm goes through and it looks at, in the before picture, for any given region, what region most closely matches it in the after image, and how must that region have translated, rotated, stretched, or skewed to get from the initial to the final state. So an example I like to show, this is just a rigid body rotation. So here's a before image. Here's an after image. You could kind of follow it by eye. And then the algorithm, it just goes through and it does that calculation a whole bunch of times over the surface. So if we compare these three techniques in terms of what measurement area, an extensometer or an LVDT gives you an average measurement over the full gauge length of the specimen. A strain gauge gives you a single measurement at approximately a point, whereas DIC gives you a distribution of measurements over a relatively large area of interest. In terms of what strain components you measure, an extensometer is going to get you the axial strain only, although certain gauges can get you the transverse strain instead. The strain gauge will give you a normal strain in whatever direction you happen to bond it, and it takes multiple strain gauges in order to get shear. Whereas DIC can give you the normal and shear strains simultaneously in every direction. In terms of contact, So an extensometer, you have to physically clip it to the side of the specimen. A strain gauge, you have to physically bond it to a specimen, which is maybe fine for one measurement, but if you were trying to get a full field distribution, then eventually as you glue on more and more gauges, you'd start to wonder, are you really measuring the stiffness of your material? Or are you measuring the stiffness of your glue and your gauges? Whereas DIC is predominantly non-contact, aside from a very thin layer of paint. And so DIC has very little disruption on the motion of the specimen. In terms of length scales, extensometer is it's averaged over the length of your specimen, so it tends to be kind of a centimeter scale. Strain gauges, it depends on how that wire pattern is printed, but it tends to be on the order of millimeters to centimeters. Whereas DIC, it depends on what lenses you use. And so I've got two examples down here. On the left is you can see an example from an electron microscope where they use gold nanoparticles to provide their speckle pattern. And then on the right, you can see a picture out of NASA where that blue thing there is a cherry picker with two guys standing on top of it, and they are manually applying paint on the outside of this big old rocket cylinder. In terms of time scales, so the extensometer, it tends to be integrated with the load frame and the load cell, so measurements tend to be on a scale of milliseconds to seconds. Strain gauges, they work kind of at the speed of electronics, so those often can get you down to microseconds. DIC, it depends on your camera. So most of the cameras I use aren't necessarily down to microseconds, although certain high-speed cameras can. And then finally, the measurement resolution. So the extensometer, the particular one I showed there, it said its resolution was on the order of about 80 microstrains. Strain gauges are very precise. They're down to about 1 microstrain. Whereas DIC, most algorithms I've seen, they boast they can get below 100 microstrains, but those are, it takes a lot of skill and a lot of art and a lot of practice to be able to get that kind of precision. So most DIC measurements, tend to be worse measurement resolution, but they make up for it with all these other trade-offs. Now, in order to perform DIC at high temperature, there's essentially 3 requirements that you need to meet. Number 1, your speckle pattern needs to be able to survive the test without discoloring or leaving the surface. And to do that, there are high temperature refractory paints out there that you can buy. White paint is rated to about 1800 degrees C. And in these results that I'm going to show to you today, we tested using a graphite specimen, which is naturally black, in vacuum up to its melting point on the order of about 3000 degrees C. Now, you do have to test in vacuum. If you were to test in air, graphite oxidizes really aggressively, and it's hard to get above maybe 400 degrees C. Number 2, there needs to be minimal heat haze, warping the air between the specimen and the camera. And so what we often like to do is use an induction heater. So this is nice because it uses magnetic fields to heat an electrically conducting specimen, as you see in the picture. So you're not directly heating the air, although the air does pick up some heat just off the specimen. But here's another advantage of testing in vacuum, is if you're in vacuum, there's no air to warp, and so you don't have to worry about this there at all. And then the third requirement is that, as you heat these things up, the specimens, they start to glow red hot or white hot. And the light emitted by the specimen can saturate the camera sensor. Now, it turns out that this light is brighter at longer wavelengths, like red and infrared, than it is at shorter wavelengths, like blue and ultraviolet. And that's not new science. That's how astronomers measure the temperatures of stars. But what other people have figured out is if you just put a blue filter on the front of your camera, you can screen out the worst of that glow, and you can continue to view your specimen surface to higher and higher temperatures until eventually you become too bright for the blue filter. And so in our lab, we took that one step further. We bought ultraviolet cameras and lenses and filters to reduce the glow even further and go to higher temperatures. So here's our test setup. So we used a Gleeble 1500D. It's got an environmental chamber for air, vacuum, and inert gas. It's got a viewing window for DIC. And that viewing window, it's a borosilicate glass, so it transmits both visible and UV light. It can do joule heating up to 3000 degrees C, although the highest we went in any of these results here is 1600. And it's got our load cell is calibrated up to plus or minus 10 kilonewtons, but in these particular slides, we're just showing thermal expansion measurements. There's no actual load. As I mentioned, we've got graphite rod specimens that are in between these two copper grips. They have a natural black background, and we applied a white refractory paint to them. And not shown in the picture, we also have a thermal camera that we was able to look down through. We cut out a portion of our glass window and replaced it with an infrared window. so we can monitor the full field temperature distribution. So our maximum temperature in these tests is about 1600 degrees C in the middle of the specimen, and then we had that cools down. There's a gradient to about maybe 800 degrees C at the ends. One of our limitations we have here is that K-type thermocouples don't go that high, right? And we need a K-type thermocouple to provide feedback control to our Gleeble. Our host from Gleeble may not like hearing me say this, but in order to kind of squeeze some more temperature out of these tests, we started out, we had one thermocouple mounted in the middle of our specimen, and then we mounted a second one over at that cooled end. And so we monitored the temperature as we heated up both of those thermocouples up to about 1250 in the middle, and we got a linear proportional relationship between those two. Then we took away the first thermocouple because it was going to be in the way of our cameras anyway, and we resumed the test, controlling off the second thermocouple. And so from that, we were able to kind of extrapolate out our temperatures up to higher temperatures than TC1 could withstand. And we monitor using a thermal camera so that we could confirm what the temperature in the middle was, what we thought it was from that linear extrapolation. So here's a bunch of images that we collected of that specimen surface. The rows are each different exposure times, and then the columns are each different temperatures. What I've plotted next to them is a histogram of each of the pixel values in each of those images. So what you can see is that as we go from left to right, as we go up in temperature, or as we go from top to bottom, we're going up in exposure time. You see that those histograms are gradually shifting towards the right, and especially as we go up in exposure time, they're also becoming wider and wider. Now here I've plotted some results. These are the average strain in each of these. So we took two images back to back. These are not thermal expansion measurements. There should nominally be zero strain. The error bars there kind of tell you the uncertainty in these measurements, just kind of as a distribution over that surface. And one thing this tells us is that depending on what exposure time you're looking at, you see saturation happen at a different temperature. So if I go up to 1300 C, using the lighting and the other particular settings in the study, we were able to continue to monitor the test over the entire range of exposure times. 1450 C, our very highest exposure time saturated, and we were unable to get an image there. And 1600 C, a few more of our exposure time saturated. We were unable to get images there. And so what we can conclude from this is that the quote-unquote maximum temperature of DIC, it depends not just on what is the wavelength of your light, but it also depends on what is the sensitivity of the camera at those wavelengths. So, well, given that different cameras have different sensitivities, we wanted to propose a simple metric that can be compared across cameras. So it's generally advised that in order to have good contrast, you should have about 50 pixel values between a typical dark pixel and a typical bright pixel. But the question is, how do you decide what's typical? And so our procedure is for each of the different images, we plot out that histogram, and then we integrate from the bottom up until we reach 5% of all pixels, and we call that Z1. Then we integrate again until we've covered 95% of all pixels, and we call that Z2. And the difference between those is the kind of the median 90% of all pixels in your image, in your region of interest, and that we call delta. And so if we plot out those error bars now, not in terms of temperature or exposure time, but now in terms of just what is that delta score, then what we find is that the correlations with a delta above about 50 tend to have less uncertainty than the ones with a delta below 50. And so this leads to our first key recommendation, is that the exposure time, it should be kept as low as possible at room temperature, while maintaining a delta of at least 50, so you've got good contrast. And that way, if you snap an image at room temperature and you've got a delta of at least 50, that means you've got plenty of room to grow as your temperature goes up. We also did a thought experiment. So suppose you took your room temperature images at one exposure time, but then you heat up your test and you learn that your images are saturated. The question we asked is, can you reduce your exposure time mid-test in order to salvage some data? So what this plot here shows is these are a bunch of image pairs. The horizontal axis is at room temperature. The vertical axis is at high temperature at each of those temperatures we just plotted before. And each little red X there is a successful correlation between those pairs. And so if we look at these, we see that if you get a low initial exposure time, you're able to maintain a correlation at a high temperature. If you get a high initial correlation exposure time, you're unable to correlate at high temperature. But by changing the exposure time, you can salvage some results, but expect greater measurement uncertainty. And I'm not showing the uncertainty on this slide, but you know, if you're interested in more, we've published a paper on that. So the threshold for whether change is possible also tends to be around a delta value of about 50. So if we dig in a little bit more into how those delta values are computed, this table is most of the images that we took, so a bunch of different exposure times, 4 different temperatures, and I've listed here the Z1, the Z2, and the delta. Again, this is our particular camera and our lights and our filter and settings. But as temperature goes up, if you pick any given row and just kind of move to the right, what you see is that the Z1 and Z2, they both go up with temperature, but they go up at about the same rate. So your delta stays about the same until your pixel starts saturating, and your Z2 maxes out at a max value of 255. So what this tells us is that high temperatures, as the images are getting brighter with temperature, they produce offsets in lighting. Now, if instead of looking across the table, if we look up and down, look at the effect of exposure time, which is our stand-in for camera sensitivity. So Z1 and Z2 scale linearly with exposure time. So if I double, then Z1 and Z2 both tend to double. If I triple, Z1 and Z2 both tend to triple, which results in a delta, which also scales linearly with exposure time. So even though temperature produced an offset in lighting, the exposure time produced linear scaling in lighting. And this has important implications for the correlation function. So I'm getting a little bit into the weeds here, but let's consider 3 different subsets. First one, F, has a roughly normal distribution and a delta of 50. Now consider G has that same distribution, but it's offset by 50. So this is as if we took a high temperature image, and now our pixel values are all 50 brighter. As opposed to H, which is twice as wide as F. So this is as if we took all those pixel values and we multiplied them by 2. So like we had twice as bright an exposure time. Well, the most basic correlation function out there is what's called the sum of squared differences. And essentially what it does is, you know, the name kind of gives it away, is you compare 2 subsets, F and G. You subtract every pixel in G from F, square those differences, and then add them all up. And if you were to do that to these subsets I've drawn here, if you were to correlate between F and G, you would see a uniform difference of 50 in every pixel. Versus if you were to correlate between F and H, because H is so much wider, you would see larger differences in the brighter pixels, and you would see smaller differences in the darker pixels. Either of these errors can lead either to a failed correlation, where the algorithm is just unable to match the correct subsets, or it can lead to an incorrect match in subsets, where it thinks the best match is at an entirely different position. All right, now the most common correlation function is what's called the normalized sum of squared differences. This is very similar. We still have 2 subsets, but before we take a difference, we normalize them by this F bar or this G bar, which is just kind of like a root mean squared. And so the effect that this has is instead of having these broad normal distributions, now they're centered around a normalized value of 1. So our subset H, which was the same as F but was twice as big, well, we normalize it, we divide it by a number that's twice as big. And so the blue curve and the black curve there, they lie perfectly on top of each other. And you know, so we fixed that. But unfortunately, our G subset, our red line there, this was brighter, and so we're going to divide by a larger number when we normalize. But the curve itself had the same width. And so when we divide that by a larger number, we end up with a narrower distribution. And so if we were to try to then correlate between F and G, what we would see is larger differences in pixels that are farther from the mean. Whereas if we were to try to correlate between F and H, which was the scaled one, we would see closer agreement between the normalized subsets. So the second algorithm, NSSD, corrects for linear scaling in lighting, but not for offsets in lighting. And then our third correlation function is what's called the zero normalized sum of squared differences. This is a 2-step normalization where in step 1, we subtract off what is the mean pixel brightness in our image. And so in this first step there, labeled C, you can see that the histograms are now centered around a mean value of 0. And then we normalize, then we divide by our root mean squared. And so that rescales the histograms that in step D there you see is all three of them lie pretty well on top of each other. And so if we were to correlate here between F and G, in step 1, by subtracting those means, now F and G agree much more closely. Whereas in step 2, by then normalizing, F and H also agree more closely. So of our three correlation functions, ZNSSD is able to correct both offsets and linear scaling in lighting. So the implications for this is that although most commercial DIC packages include all three of these functions, they often choose the middle one, the normalized SSD by default. But in our case, because the light emitted at high temperature creates offsets, we should always adopt the zero normalized, the third function, when performing DIC at extreme temperatures. So why not always use ZNSSD? Well, number one, the fact that we've got that extra zero offset step, it can add to the computation time. And depending on how large your data set is, how high the resolution of your camera is, how many images you're trying to correlate, that can add up pretty quickly. And then number two is if you don't have a reason to need it, then by having that extra step in there, you could be overfitting your data to perceived errors that aren't actually there. Now to close out this talk, I'd like to talk about an application we've been working on with NASA, and that's hot fire engine testing. And so what you'll see in that red box is a strain gauge, and it's the nozzle heats up right there, it just snapped free of the specimen. Whereas they've also speckled it with paint, so they're able to continue to monitor at temperatures well above which the strain gauge has failed. But now you can see that as they heat up hotter and hotter, now the nozzle is starting to glow brighter and brighter, and that glow is interfering with the camera. Now here's a few still images from a similar test, and what we see in these is we started out with a pattern that had initially dark background with a little bit lighter paint, and then as the nozzle heated up and as it started to emit light, the background actually started to emit more light than the paint. And so we ended up with this pattern where the final pattern appeared to be inverted relative to our starting pattern, and that confuses the correlation algorithm. Now, it turns out that this speckle pattern here, we like to think of it as a superposition of both reflected and emitted light. And so if you think of your initial paint, your initial reflected light is kind of those green bars down there. We've got a little bit brighter paint over a dark background. And then as the temperature moves to the right, as the nozzle heats up, the background starts to emit more and more light until eventually the background becomes what's brighter than the paint. So our challenge here then is how do we mitigate this? So we came up with a test plan. For our first method, we took 4 quasi-static images. First at low temperature with the lights off, we took an image. And this contains no light, so there's no reflected, no emitted, it's just nominally dark. Then we flip the external lights on, and we're at low temperature, so we're not emitting anything, but that image A2 contains reflected light. Then we heat up the specimen with the light still on. We take another image. This image contains both reflected and emitted light. It's that superposition we just talked about. And then we flip off the exterior lights. And so now there's nothing to reflect. And the only light being picked up by the camera is the emitted light. Then we can post-process those images. Take images A3 minus A4. And if you've got something with reflected plus emitted and you subtract out all the emitted, that gives us an artificial image that's reflected only, but contains knowledge of the thermal strain. So we can actually measure the thermal expansion without that inversion. Then to compare this, test B, we used our UV cameras and lights and filters. And so here, we took the same 4 images, lights off, lights on. And at room temperature, they look more or less the same. But at high temperature, the filter screens out that emitted light. And so image 3 works just fine, and it doesn't require any post-processing. Now to compare these two techniques, it took a little bit of a flow chart. So as our reference image, we used image A2 there. And in the top row, we correlated that against our artificial image, A5. But then in test B, because we had that filter, the filter has a little bit of a thickness to it, and that glass creates a distortion in our images. So first we have to correlate our 2 room temperature images against each other, A2 versus B2. Then we correlate A2 versus B3. And that gets us our high temperature measurements in the same coordinates for both systems, and then we have to subtract the two B correlations to get rid of that thick glass displacement. And so those are the two results that we then compare between test A and B. So here's our results. Method A with the subtraction method. Here's where we had our artificial images. We produced that image A5 down there at the bottom. Here's our method B with the UV filter. So here the filter effectively screens out that glow. We don't have to worry about inversion at the high temperature. And then here's the strains that we measure off those images. And we see that the strains, they agree more or less with each other. They agree within about 5 or 10%. It tends to be a little bit worse at the edges, but DIC just in general tends to be better towards the interior of the speckle pattern. Once you start reaching the edges of the region of interest, you've just got less subsets in order to make your strain calculation. So both of these methods, they yield comparable results, but they both have drawbacks, right? So method A is our subtraction method. And the problem with it is it requires two different images with no motion between them so that we can subtract them to get rid of the emitted light. And so that means that method A only works for quasi-static. Method B is okay, there's no subtraction, it works with single images, but our UV camera is a relatively slow frame rate, about 40 frames per second. So I mean, that's better than quasi-static, but it's probably not good enough for all the shaking and vibrating going around in that hot fire test. So our next question was, can we make this any faster? First, we wanted to tackle the UV. And so we bought a high-speed UV amplifier, which is this device you can kind of strap onto the front of a high-speed camera. And it has these phosphors in it that effectively convert UV light into visible light so the camera can look at. So we took this system and we strapped it on top of our Gleeble. We looked down into our viewing window. So setup A on the left there has no amplifier, and setup B on the right has an amplifier. We produced these images of our graphite specimen up to 1600 C. So without a filter, we inverted in between about 800 to 1000 C. And we completely saturated by 1600. Whereas using the amplifier, we were able to see over that entire range. Then we measured strains off those images, and at a lower temperature for which both methods work, I would say that the measurements are fairly comparable. They're about the same magnitude. But it's at 1600 C, the UV method's able to go to even higher temperatures. Next, we wanted to apply this to a high-speed problem. So we moved to a different specimen outside our Gleeble. This is a vibrating plate. So you can see a simulation of the mode shape on the left, and in our lab, this particular plate's useful for certain fatigue measurements that we do. And so we've got the camera on a tripod is looking at that plate as it's vibrating, and it's looking at the free edge in particular as it flexes up and down. So at room temperature, we get, once again, we get comparable results. The amplifier is noisier, but comparable. And then at high temperature, the amplifier is able to see things at both high speed and high temperature that the room temperature result was unable to see, that the unfiltered method was unable to see. So I would say both techniques are comparable at room temperature, but the amplifier works to the higher temperatures, even though it's noisy. These results are about to be submitted to review of scientific instruments. Now circling back to our other method, method A, where we subtracted images. We said the drawback there was that it only worked in the quasi-static cases where there's no motion between the lights on and the lights off images. So we proposed a new solution for that as well, is let's use blue lights and a color camera, and it produces those images there. So this breaks down our test matrix. The color camera is effectively 3 sensors that overlap with each other, a red, a green, and a blue channel. And so the table looks messy, but I've circled the 3 that matter. Is at low temperature, we've got our image A2B, which I've circled in blue, which contains only our reflected light. And at high temperature, we've got this image A3G. So this is the high temperature image out of the green channel, but because we're using blue light and we're recording with a green channel, that green channel isn't picking up anything reflected. It's only emitted light. And so our goal then is we want to post-process that image using our knowledge of what A2B looked like at room temperature to create an artificial A3B that doesn't have any of the emitted light in it. And so the key assumption that we used here is for any given pixel, the brightest 5% of pixels at room temperature are going to contain the same area fraction of paint is the darkest 5% of pixels at high temperature, and vice versa. And not just 5%, but we repeat that for all the other percentages as well. So just a schematic of that process. First, we make a histogram of our before and our after images up there. Then we integrate them, so we get these cumulative histograms. And so for any given value on the green curve, we assume that that has a particular area fraction of paint. And so we go find that same area fraction on the blue curve, and we reassign that pixel value to create this artificial image here. So this approach, it mitigates the inversion without having to subtract images, which means that we're no longer limited to quasi-static cases. And the results of this are about to be submitted to the journal Strain. So just to summarize, DIC can survive much higher temperatures compared to other contact measurements, such as strain gauges. You can use blue or UV filters to screen out the emitted light off the specimen at extreme temperatures. And the maximum temperature of DIC, it depends not just on which wavelength of light you use, but also the sensitivity of your camera. So there's papers out there, not by my group, that have used blue DIC up to 3,000 degrees C, right? And so this isn't a blue versus UV thing. It really is about what camera settings you use. Number 4, we propose this delta metric. It's a quick and dirty way to quickly assess image brightness to figure out, are you going to saturate? It takes about 4 lines of MATLAB codes. You just snap an image at room temperature, make sure your camera sensitivity is as low as possible while maintaining sufficient delta. So you want a delta of at least 50, and you want to make sure that your Z2 isn't saturated. And then based on delta, we also observed that the emitted light off the specimen produces offsets in lighting, but the camera sensitivity, so changes in exposure time, produce linear scaling in lighting. And so based on that, we also recommend that you always use that ZN SSD criterion when testing at extreme temperatures. And this may involve in your DIC software having to find a drop-down menu and switch which correlation function you're using. We also discussed speckle pattern inversion. This is a special case where for certain pairs of speckle materials, the initially dark material might glow brighter than the initially light material. But the speckle pattern that results is a superposition of a reflected and emitted light. So we presented essentially 3 approaches to resolve this. Method A was to subtract a lights off image against a lights on image. But this is limited to quasi-static measurements. Method B is you can apply either a blue filter or a UV filter. A drawback here is UV cameras are relatively slow unless you use an amplifier, which tends to be pretty noisy. Blue filters are pretty cheap though. You can get a good one for a couple $100, which I mean that's much cheaper than the cameras and the lenses and the lighting and the rest of the test setup. So if you have the option to buy a blue filter, then by all means do that. And then method C we presented there was blue lights and a color camera. And so from this, we can artificially de-invert the image using knowledge from that green channel. But anytime you're creating artificial images, you just want to be very careful not to corrupt your measurements. Now, like any professor, I'm only as good as the students that I have working for me. I've had quite a few over these past 5 or 6 years. Most of this work that I presented today is from a PhD dissertation by Tin Tai, who graduated last year, and he now has a faculty position in Vietnam. The rest of the work, those last few slides there, are by Lindsay Rowley, who's a MS student who's going to be defending in a couple weeks, and various lab mates that have helped them along the way. So with that concludes my talk. Thank you for your attention.